Hello guys, welcome on Tesla Adventures. In this video, we are going to discuss the formula for torque acting on a current carrying loop which is placed in magnetic field. So you can see that this is a current carrying loop which is placed in magnetic field, and magnetic field is making some angle theta with the plane of the loop like that, and current is flowing in this direction, and you can see that the force acting on the wire BC will be, if you will see the direction of the force acting on the wire BC, then it would be you can see if you will take the components of the magnetic field, one is parallel to the wire, one is perpendicular to the wire, and then you will apply the Fleming's left hand rule, then you will see that the force will be acting on this wire in the downward direction, FBC. Just take a component of the magnetic field along the wire and in the perpendicular direction to the wire. You will notice that the component of the magnetic field which is along the wire will not produce any force on the wire, and the other component which is perpendicular to the wire will produce a force acting on the wire in the downward direction. And in the same way, the force will be produced on this wire dA in the upward direction. And obviously these two forces will be equal. FBC will be equal to FdA in magnitude, and therefore the net force acting on BC plus force acting on dA will be 0. Okay, and now if we discuss about the force acting on wire CD, to discuss this fact, you must notice that magnetic field is perpendicular to the wire CD. And in the same way, the magnetic field is perpendicular to the wire AB. And if we have to discuss this force, we have to view the top view. You can see if we are viewing this wire from the top, from this position, then we will visualize the edge BC like that, tilted, and current will be flowing from B to C. Now if we have already discussed that force acting on the edge BC and DA is 0. They are cancelling out each other, and the force acting on the wire CD, you can see that this current is going inside this plane from C to D, and therefore if we see the magnetic force acting on the wire CD, then it would be like that, FCD. And in the same way, this current is coming out of this plane from A to B, from this point, and therefore magnetic force will be acting in this direction, FAB. Now FAB will be equal to FCD, and this F is, if this is the length which is B, then this F will be equal to I, and L is B and magnetic field is B. Here we will take the complete net magnetic field, because the net magnetic field is perpendicular to the wire, so we do not need any component of magnetic field. Okay, now we see that the net force acting on the loop is 0, obviously, because these two forces will cancel out and those two forces will cancel out. But these two forces will create some torque about the center. So the torque can be calculated by a simple analogy. Torque will be, if this is F, then torque will be F into A by 2 cos theta and into 2, because there are two forces which are producing the torque in same sense. So torque will be equal to FA cos theta, and F is IBB, so IABB cos theta. This is the torque. Now we know that this is the area, A into B is the area of the loop, so it would be IAB cos theta, and I into A is magnetic moment of the loop. So this will be m into b cos theta. And now if we draw the direction of m, then you will see that m will be in this direction, like that. Magnetic movement will be in this direction, because magnetic movement is always in the direction of area vector, which is perpendicular to the loop. And this angle, the angle between magnetic movement and magnetic field, is this one. So this angle is alpha, let's suppose, and alpha is equal to 90 plus theta. So theta will be equal to 90, in fact theta will be equal to alpha minus 90. So torque will be equal to mb cos 90 minus alpha, because you know that cos alpha minus 90 is equal to cos 90 minus alpha, and tau will be equal to mb sin alpha, and in vector form you can write down it as m cross b. Many of the students are wondering that why I have converted this angle, because obviously when you are writing m cross b, and when you will open m cross b, then m cross b will open as m modulus b modulus sin theta, where theta should be the angle between m and b. So the angle between m and b is alpha, so I have to convert this angle theta to alpha, and then I can write it down in cross product form. So this was the formula for this loop. And if we discuss the equilibrium positions of the loop, then obviously when the direction of m and direction of b will be parallel to each other, theta will be 0 degree, then it will be stable equilibrium. And this topic will be discussed in detail in the upcoming videos of magnetism in matter, in bar magnets. So this will be stable equilibrium. Why I am referring it as equilibrium? Because torque is 0 in this position, and in this position it will perform SHM. So if we find out the time period of small SHM of the loop, then obviously we know that torque is m b sin alpha, and for small angles torque will be equal to mb alpha, and torque is equal to I alpha, and this alpha is omega square theta, where theta in this case is alpha. That when we write torque as I alpha, then this alpha is angular acceleration, and this alpha is the angle which I have taken. So don't get confused in that. So cancelling this alpha with alpha, and I is the moment of inertia about the axis of rotation. So omega will be equal to under root mb upon I, and omega is 2 pi by t. So t will be equal to 2 pi under root of I by mb. So this will be the time period of a small SHM of the loop. If the angle between m and b is 180 degree, they both are opposite, then this is torque is still 0, but this is unstable equilibrium. And again this topic will be discussed in detail in bar magnets, in magnetism in matter. Thank you.